Okay, on page 900, we're going to look at properties that you've been using since probably 5th or 6th grade. I know you used in pre-algebra and algebra. Identities, or identity properties, commutative properties, associative, inverse, distributive, and properties of equality. Just the ones on the left is what we're going to look at today. And I'm only really going to talk about the ones that we're going to use instead of trying to do too much right now. We're just going to skip to the commutative properties and associative properties. Well, we're just going to skip the identity because that we really don't use. So commutative property, a plus b equals b plus a. That's like 3 plus 5 equals 5 plus 3. So you're able to swap that out. Also with multiplication, 3 times 5 equals 5 times 3. Associative, you can regroup when you're adding. It doesn't matter what order, and when you're multiplying. But if you have a mixture of that, you can't do it. But so that's what associative is. Inverse. Inverse property, if you have, let's say, 2x plus 3 equals 11. The inverse property is what you use when you try to get rid of numbers that are on the same side with x. Because when we solve this equation, we try to get x by itself. So you would use the inverse of 3, which is negative 3. Okay? The property that allows us to subtract 3 from both sides is the subtraction property, which you'll see below the properties of equality. So the inverse is what we're using, but the subtraction property is what we're actually doing to get to this. So this is the subtraction property. To get from this to this, we're dividing by 2. So we're using the inverse, which is dividing by 2 since it's being multiplied by 2, but what we're actually doing is the division property to get to x equals 4. Okay? So the additive and multiplicative inverse, the additive inverse and multiplicative inverse, that's what we're doing. That's the numbers that we're using, not what we're doing. The numbers that we're using to get rid of it, and the actual process of doing it is the subtraction property and division property that allows us to actually go through that process. All right. So distributive property, you know how to distribute. If you have something outside the parentheses, and as long as everything inside parentheses is simplified, you distribute that inside parentheses. The properties of equality, a equals b. If a equals b, then a plus c equals b plus c. So that means you can add c to both sides. Subtraction, you can see that they're subtracting c from both sides, which is what we did here. Multiplication, if you multiply both sides by c, then you still have an equation that both sides are equivalent. So that would be multiplication property, division property, dividing by the same number as long as the number is not 0. You don't want to divide by 0. Substitution, if a equals b, then b can be replaced in any expression for a. So if a equals b and you have a equals 5, well, b equals 5, right? Because they're equal to each other, if they're equal to each other. Reflexive property, a equals a. That's kind of hard to, you probably think, well, why would you need a property that says something is equal to itself? Well, there's a reason, and you'll see as we do geometric proofs. Symmetric, if a equals b, then b equals a. Now that may look similar to, what was it? No, it doesn't. If a equals b, then b equals a. So that's similar to if I wear a size 8 and you wear a size 8, then my size is equal to your size. I'm talking about shoe. And then you could, if that, then I could say if you wear a size 8, then I wear a size 8. If our sizes are equal. So you can switch that around. All you're doing is switching the amounts on either side of the equal sign. Okay, transitive. Okay, transitive, if a equals b and b equals c, then a equals c. What that's saying is, if I wear a size 8 shoe, you wear a size 8 shoe, we wear the same size shoe, and I go, okay, you and Andrew wear the same size shoe. What does that mean about me and Andrew? We wear the same size shoes. That's transitive property. That's showing that you and I wear the same size shoes through another person. Because I didn't say that we wear the same size shoes. I say I wear the same size as she does. She wears the same size as you do. Therefore, we wear the same size. So that's transitive property. All right. Turn to page 902. 1.1, I call it 1.1, it's 1-1. If you'll recall, what I'm going over now is all of not all of them, the ones you really, really need to know, postulates and theorems in chapter 1 and chapter 2 in order for us to do what we're going to be doing in this section, or the rest of the chapter. 1.1 through any 2 points, there is exactly one line. Do you remember when I used the mints in the floor? I said if I have 2, there's only one line that goes through those 2 points. You can define a line with 2 points. Okay, if 2 distinct lines intersect at one point, not at one point, if 2 distinct lines intersect, then they intersect at exactly 1 point. We talked about that. If 2 planes intersect, they don't form a point, they form a line. Remember, because here you've just got 2 things forming a point. But if this slices through each other, you can see that there's a line where they're connected or where they intersect. Through any 3 non-collinear points, there is exactly 1 plane. I showed you that with the 3 mints on the floor. How if they're all in the same line, there's an infinite amount of planes that can go through that. But if you just take one of the 3 and move it off of that line, then you have exactly 1 plane. Every point on a line can be paired. Okay, ruler postulate, we're not going to use that. Segment addition. We will be using segment addition a pretty good bit. Remember, if you have one long segment and it's broken up into 2 segments, this segment plus this segment is equal to the whole segment. We also do that with angles, which we'll talk about in a minute. We're not going to do protractor postulate. Angle addition. So if I have a big angle, and inside that big angle I have a ray, cutting that big angle up into 2 different angles, those 2 smaller angles, when I add them together, are equivalent to or have the same measure as the big angle when I add them together. Okay? Midpoint formula you use, distance formula you use, except for I showed you shortcut. Area addition postulate, you're not really going to use that now, maybe later. Chapter 2, let's go down to the reflexive, symmetric, and transitive properties. We already talked about that on page 900. Reflexive, symmetric, and transitive. That's what I was talking about, same size shoe. Reflexive, I wear a size 8, my shoe size is equal to my shoe size. Which is weird, I know, but that's what it is. That's reflexive. Symmetric, my shoe size is equal to your shoe size. Your shoe size is equal to my shoe size. Transitive, my shoe size is equal to your shoe size is equal to his shoe size, then and that implies that we wear the same shoe size. So that works with segments and angles. If my angle that I draw on my paper is equal to the angle on your paper, and the angle on your paper is equal to the angle on his paper, then ours equal. Okay? So it works with segments and angles. Vertical angles theorem, that just states that vertical angles are congruent. We will be using that at some point. Theorem 2.2, congruent supplement theorem. If 2 angles are supplements of the same angle, or congruent angles, then the 2 angles are congruent. Well, what does that mean? Sometimes the words, it's really hard to figure out what's really going on. What that's meaning is, if I have this angle here, and if I tell you this angle is a supplement to this angle, and I tell you this angle is a supplement to this angle, if they're both supplements, they have to be congruent to each other, right? You could also say that in reverse. That's why it's a theorem. If this angle is congruent to this angle, and this angle is a supplement of that angle, then this one is too. Has to be. Same happens with complementary angles. Theorem 2.3. Theorem 2.4. All right angles are congruent. Do you agree? Are all right angles congruent? All right angles are 90 degrees. All right angles are congruent. Have to be. And believe it or not, we do need that theorem. Last theorem we're going to talk about today. If 2 angles are congruent and supplementary, then each is a right angle. Think about that for a second. The only way two angles can be supplementary and congruent at the same time is if they're 90 degrees. Does that make sense? The only way they can be congruent and supplementary at the same time is if they're 90 degrees. You have one of those homework, one in your homework problem the other day, where it said supplementary angles cannot be congruent, and the counterexample was two right angles are supplementary and they're congruent. Okay. All right. So you need to write this down in your notes. Just this part. You don't have to do this part. The lesson 2.5 reasoning in algebra and geometry. Got it? Okay. Gotta go through and erase some stuff. Okay. So the first thing we're going to do is practice justifying statements so that we can do proofs later. So name the property that justifies going through the first statement to the second statement. So look at A, 7x plus 3 equals 24. How can you go from 7x plus 3 equals 24 to 7x equals 21? What do you have to do to get it from one step to the other? Yes, that's correct. So if we're subtracting 3 from both sides, look on page 900. If we're subtracting 3 from both sides, what property are we using? Listen to the words. When you're subtracting the same number from both sides, we're using the what property? When you're subtracting the same thing from both sides, the subtraction property. Look toward the bottom, properties of equality. Do you see how they're subtracting C from both sides? We're subtracting 3 from both sides. So to get from here to here, you have to use the subtraction property. Okay. If RS equals ST and ST equals TU, then RS equals TU. How do we go from this step to this step? Which property? Yes, good. Transitive property. Part C. 5x equals 10, 10 equals 5x. Symmetric, good. All right. So you'll have homework problems where you're having to determine what property is being used from one step to the next. You're justifying those steps. Okay. Here we're going to work this problem just like a problem you worked in chapter 1. So you already know how to work the problem, but with each step we're going to justify the step. We're going to put a reason next to each step. Since this is not a formal proof, we're just going to start out with the equation. The equation is, we know that x plus 2x minus 15 equals what? They're a linear pair. What do they equal? 180. Good. Instead of writing x plus 2x minus 15, let's go ahead and combine that in our head. Can we do 3x minus 15? Would that be confusing? Do you understand why it would be 3x minus 15 equals 180. And I'm going to say that that's the given information. This is the given information in the figure. If it's a formal proof, there would be more to this. So on the next step, normally we would add 15 to both sides. We would show that, but let's not show it. Let's just do this. Because I'm trying to teach you how to see it without showing it. What property allows us to add 15 to both sides? Add 15 to both sides. We're adding 15 to both sides. Addition property. See, the addition, subtraction, multiplication, division property should be easy because it's what you're doing. If you're adding to both sides, then it's the addition property. Okay, next we're going to divide both sides by 3. So when I divide this side by 3, I'm not going to show it. And when I divide this side by 3, I get 65. What property allows me to go from this to this? From 3x equals 195 to x equals 65. What did we do? What did we have to do to get rid of the 3? Divide. We divided by 3. So the division property. I've got to check something real quick. Okay, this one's right up. All right. So that's more of an algebraic type proof. Next proof we're going to do is geometric. Is anybody still writing that? Next is geometric, and it's not as straightforward. On a 2-column proof, you need to always write the given, the proof, draw the figure, everything that I have here. You don't leave any of that out. Now, you don't have to write the directions up here, but you write down the given, the proof, draw the figure, and then have your chart set up for your 2-column proof. Now, before we even discuss how to prove this, we're given this information. This should be our first statement. This should be our last statement, because it's like we have the answer to the problem, but we're starting with the problem, and we've got to prove that that's the answer to the problem. So statement 1, you have to number it. AC is equal to BD. The reason that AC is equal to BD, we don't have a reason other than that's the given information. The first reason is always given. The last statement, we're not going to write yet, should be this, because that's what we're working toward. We're trying to make that turn into that. So the given information is telling us that AC is equal to BD. If they're equal to each other, then we have to prove that this is equal to this. AB is congruent to CD. Just by knowing that these two overlapping segments are congruent to each other, we've got to figure out how we know that AB is congruent to CD. I'm going to draw my two segments separately. This is congruent to this. Well, we see that these are the same, so these two should be the same if the whole thing is the same, right? So the first statement we're going to make after the given information, which will be statement number 2, is that we know BC is congruent to BC, or equal to BC. What property allows us to say something is congruent to itself? Reflexive, good. So we know this is congruent to this, but how does it make these two congruent to each other? This is where it gets a little confusing. I can set up an equation saying AB plus BC equals AC. AB plus BC equals AC. This plus this equals this. I could say the same thing about the other segment. BC plus CD is equal to BD. Since they're both using the same property, because they're both the same thing, I can put the two things together in one statement. What property or postulate allows me to say that AB plus BC equals AC and BC plus CD equals BD? You'll have to turn to page, I think, 902 for that one. What am I doing to my segments? I'm adding them together, right? Look for something with segments and adding.
Segment addition.
Yes, segment addition. Property. All right. So, how can I turn this into this? Well, if AC and BD are equal to each other, and I have something here that AC is equal to and BD is equal to, could I substitute this in for AC and this in for BD in this sentence or equation? I can. I can say that AB plus BC is equal to BC plus CD, correct? If these two are equal to each other, then these two are equal to each other. What property did I use? I used the word when I was describing what I was doing. What did I do? Substituted. I substituted this in for AC and this in for BD for this. Okay, well, my goal is to get this. And if you see, this equation looks like this, except for there's BC on both sides. Can I get rid of BC? I can subtract BC from both sides, and what does it do? Just disappears, right? So I can say at this point that AB is equal to CD. And the property that allows me to do that is subtraction. I subtracted BC from both sides. You may be looking at this and going, how in the world am I going to do this? Well, fortunately, turn to page 116 and 117. Fortunately, look at number 4, look at number 5, look at number 7. They're doing the work for you, and you're just stating the property. Number 9, you're stating the property. Number 11, the property. Number 13 looks similar to what I just did, but look, you're just filling in the blank. You're not having to do it on your own. We're taking baby steps here. We'll get you to where you can do it on your own. So we're filling in blanks. You only have one problem, like what I just did here, where you're doing a formal two-column proof, and that's the very last one, 23. So let's look at it. On 118, number 23, fortunately, that problem's easier than the one I did because you're doing algebra. You're setting up an equation. So you're doing a formal two-column proof where you're setting up an equation. Do the best that you can do. If you need help, we'll look at it tomorrow. If we look at that problem, that's the only one we'll have time for before we do another lesson. Okay? So, there's your assignment. And you have about 15 minutes. So you can get my help, which would be pretty good in this section if you need it.